This week we're going to be learning about work and energy, and this starts a whole new unit where we're going to look at the way that objects move in a completely different way than we've done in the past. So in the past what we've done is we've looked at kinematics, which relates an object's initial velocity, final velocity, acceleration, change in position, and time. And we've looked at dynamics, which involves what forces are acting on an object. And we use both of those tools to help us describe, what's going to happen to an object when forces act on it. We are going to be answering the same types of problems now, but we're going to use a completely different method because we're going to consider what type of energy the object has and how much energy the object has, and whether there are forces doing work on the object. So we're going to be solving a lot of the same type of problems, but with different equations. And a lot of people find these equations to be easier than the kinematic equations that we used previously. So first we need to start to understand what energy is. And energy is kind of, in the beginning, it's a tricky concept, but I think the best way to understand what energy is to look at a bunch of different types of energy, and then we can talk about how energy is transformed from one type to another. So here are some of the types of energy that we look at as physicists, and some of them we're going to talk about this semester, some of them you'll talk about in the second or third semesters of your physics classes. So the first type of energy we're going to talk a lot about this semester is shown here in this picture, and that's mechanical energy. So whenever an object is moving, or it might move if you let go, the object has mechanical energy. The type of energy depicted here is thermal energy. Anytime something is hot, it has thermal energy. If something gets hotter, we would say that its thermal energy has increased. Here I'm showing electromagnetic energy, and this is a type of energy whenever you are using electricity, you're using electromagnetic energy. And this is a topic that you're going to study a lot in the next semester of physics. There is energy stored here. It even says it right here on the can. And the type of energy contained in energy drinks and really any type of food at all is called chemical energy. So the molecules in food, or anything that has calories, the molecules in there can be broken apart by your body, and your body can use the energy that is given off by those molecules when their bonds are broken apart. And finally, we have nuclear energy. And similar to chemical energy, the bonds within a nucleus, okay, so the bonds of the protons and the neutrons together in a nucleus store a lot of energy, and when you break apart those bonds, a lot of energy is released. So that type of energy is called nuclear energy. This is something that you'll learn about in Physics 3. In this class, we're mostly going to be talking about mechanical energy and a little bit about thermal energy. The units that we're going to use to describe energy are joules. Okay, so we use a big capital J to describe joules. And later we'll look at, how can we break joules down into other units. But for now, I just want you to think that all energy is measured in joules. Another unit of energy that we do not use in this class, but that you probably use in your daily life, is a calorie. So a calorie is a measure of energy. And so when you look at the calorie content of some type of food, that's actually telling you how much energy there is in that food that your body is going to then turn into another type of energy. So let's look a little bit more about mechanical energy. There's two types of mechanical energy. One is kinetic energy, which we call the energy of motion. One is potential energy, which we call the energy of position. So let's focus a little bit on kinetic energy. Next week, we're going to learn a lot more about potential energy. So kinetic energy is the energy of motion, and I just want you to think anything that is moving has kinetic energy. So no matter what the object is, if it is moving, it has kinetic energy. Potential energy is something that's in a certain position, and it might be moving, it might not, but if it's not moving, but it's in a position where if you let go and it does move, then that object has potential energy. So you can think potential energy is like the potential to have kinetic energy. So for example, if you hold your keys, high up off the ground, and you're just holding them out and you're kind of dangling them, the keys have potential energy. They're not moving right now, but if you let go of your keys, they would fall to the ground, and once they start moving, they do have kinetic energy. So just holding your keys up high gives them potential energy due to their position. And like I said, we're going to talk more about potential energy next week, but for now, we will definitely keep talking about kinetic energy. Okay, so let's just for a second compare a smart car to a big, what's this, Escalade? And let's say they both are traveling at 70 miles an hour. Which one of these do you think is using up more energy in terms of the gasoline that it's using up if they're both going 70 miles an hour? I think you would all agree the Escalade is definitely using up more energy. So you kind of probably have an idea in your mind that the kinetic energy these objects have depends on their mass. Okay, so that when this car is going at 70 miles an hour, it's using up a lot less energy because it's a lot less massive than when this car is going 70 miles an hour. And if that makes sense to you, that's correct. Our formula to calculate the kinetic energy of an object is simply K. So K is the variable that we're going to use to represent kinetic energy. K is equal to 1/2 mv squared, where m is the mass of our object and v is the speed of our object. So this is why I say anything that is moving has kinetic energy. How much kinetic energy does it have? 1/2 times the mass times the speed squared. And this equation, we're going to be using this all the time. So one important property of energy that can also help you understand what energy is that energy is conserved. Okay, and conserved simply means that it cannot be created or destroyed. So you can't just suddenly have energy appear out of nowhere. If it were possible to have energy appear out of nowhere, then we wouldn't have all the problems we have, with our energy crisis. We wouldn't be burning fossil fuels in order to get energy if it could just appear out of nowhere. The reason we burn fossil fuels is that we want energy, and we're getting it by breaking the bonds in our fossil fuels that releases the energy, the chemical energy stored in those bonds, and then we use that for whatever we want. So energy cannot be created or destroyed. It can be transformed from one type to another. Okay, and so a good way to understand energy is to look at how energy is transformed, how it turns from one type of energy into another type of energy. So let's just consider, for example, this race car. Okay, right now it's driving really fast. It has a lot of kinetic energy, and we can try to figure out where does that kinetic energy come from. Okay, so the car has kinetic energy, and I can just say, where is that kinetic energy coming from? It has to come from somewhere because it can't just appear out of nowhere. Well, the kinetic energy of the car, we could say, came from the chemical energy of the gas. So the gasoline in the car stores a lot of chemical energy in the bonds, the gasoline, when you break the bonds, when you burn the gas. It releases the energy that's stored in those chemical bonds, and that energy is turned into, eventually, it's used to move the pistons up and down the car, but eventually it's going to be turned into kinetic energy of the car. We can also, though, just ask ourselves, where did the chemical energy of the gas come from, right? Where does gas come from? Well, it's kind of a joke to say dinosaurs, but it comes from life forms that lived millions and millions and millions of years ago. And so we'll just, as a joke, say it came from dinosaurs and dinosaurs turned into gasoline. But it's not too far-fetched to say that. But life forms from millions of years ago, after they die, their body decomposes, and the carbon and the hydrogen, forms these things we call fossil fuels, which is what gas is. So then we can say, well, where did the energy from the dinosaurs, right? I mean, dinosaurs are walking around, they're living beings. Where did their energy come from? Where did they get energy from? They get energy from the food they ate. Okay, where did the food that they ate get energy from? Well, if they were carnivores, that came from other dinosaurs. If they were herbivores, their food were plants. So we're kind of saying, where did those plants get their energy from? They got their energy from the sun. Okay, and whenever you trace where did the energy come from, back as far as you can go, and we're talking about something on the earth, you're always going to end up at the sun. So all the energy of all these things we have on the earth, the energy from that comes from the sun. If we want to know where did the sun energy come from, I would say that came from the Big Bang. And before that, who knows what happened. Okay, so this is just a useful little exercise to go through to help you understand what energy is.